Hello, I'm Jeremy Gibbons, and I'm going to talk to you about how to design co-programs. So one of the problems that beginning programmers face is where to start. Where do my programs come from? I've got a programming problem to solve and a blank editor window in front of me and no guidance on where to get started. So one of the things we do is give them that guidance. We tell them to start by analysing the structure of the input you're going to consume. So for example, if you're writing a program to consume a list is either empty or it's not, so you'll have a case for empty lists and a case for non-empty lists. A non-empty list has a head X and a tail X's, and you're probably going to need those in the solution, so you already have some part of the structure of your output, of your program. More than that, lists are recursively structured. The tail of the list is another list, and so you can make a recursive call on that tail and use that in your solution too. So you get a more refined template for your program, where in the non-empty case you can use the head X, the tail X's, and the result of a recursive call on the tail H of X's. So this lesson, that program structure follows data structure, is a key lesson in introductory programming, and it's a central message of the very influential textbook, How to Design Programs. This book is built around a collection of design recipes, like the structural recursion that we've just seen. So let's look at those in a bit more detail. If you're writing a program that consumes some composite data, like a record, the advice is to name the components of that composite data. So here we're consuming a playing card. A playing card has a rank and a suit. We're probably going to need the rank and the suit in our solution. So let's start by naming them. R is the rank, S is the suit, and now we have to do something with R and S. Dually, if your input data is of a mixed data type, there are several variants. The advice, the design recipe, is to enumerate the alternatives. So here's a more refined model of a playing card. It's either a regular card as before with a rank and a suit, or it's a joker. And if we're consuming one of these cards, well, we enumerate the alternatives. It's either a regular card, in which case we do the regular card thing, which was the previous problem, or it's a joker, in which case we have to do something else. And then there's structural recursion. If your input data is inductively structured, like lists, the design recipe is to use structural recursion, as we saw earlier. So if you've got the problem of sorting to solve, and you hit it with the design recipe for structural recursion, you're led inexorably to a particular sorting algorithm, to insertion sort. So you consider the input, it's either empty or it's not. If it's empty, of course, you sort to get the empty list. Otherwise, it's non-empty with an X and an X's. You can make a recursive call on the tail X's. So now you've got the head X and the sorted tail. What are you going to do? Well, you have to insert the head into the right place in the sorted tail. So that gives you the main function. ISort xcons x's is insert x into ISort x's, and the only problem now is to define insert, which you can do by using the same techniques as on the sum problem. So this is all well and good. It's good advice for students. It helps them in designing programs, but it's only half the story. It's only half the story because it's only considering the input data structure, and the output data structure might be useful too. And I think it's missing a trick not to exploit that output structure and not to give the hint to students that they should do so. So let's look at those design recipes again, but from the other side, for looking at them from the perspective of output data structure. So now we're not consuming but producing a record. So here we're producing a date. A date has a day field, a month field, and a year field. So we're going to have to come up with a day and a month and a year. So let's name those. Let's have one subprogram per field, name those subprograms D, M and Y, and then we have to construct the record out of dm and y. Dually, if you have to produce variant data, enumerate the alternatives. So here's a safe division problem. You want to compute x divided by y, unless y is 0, in which case you have produced some separate value instead. So in Haskell, the idiomatic way to do that is with the maybe data type. Values of type maybe integer are either nothing or just an integer. And safe division, of course, if y is 0, it produces nothing, otherwise it produces just the quotient x divided by y. So what is the structure of this program? Where did that structure come from? If I couldn't immediately see the program, how can I make a first step towards it? So of course there is a case analysis, and there is a case analysis on the input, y. But it's not a case analysis determined by the structure of the input, because here y is not a structured argument. It's not a record, it's not a list, anything like that. Instead, it's a case analysis on the value of the input y. So this is not following our advice about considering input data structure. So that doesn't explain this program. Instead, of course, it's the output data structure that explains the program. The output data structure is a maybe, so it's either a nothing or a just, and the program structure has branches for the nothing case and the just case. So considering the output structure is a much better explanation of this program. And if you wanted to give a struggling student a hint based on structure, then it has to be the output structure you give the hint about. And then inductive data. So again, this is list, but now you're producing one, not consuming one. What are you going to do? Well, a list is either empty or it's not, so you have a case analysis. Under some circumstances you produce the empty list, and otherwise you produce a non-empty one. And if you produce a non-empty list, of course you have to produce its head x and its tail x's. But more than that, the tail is another list, so you could do that by making a recursive call. So a more refined pattern, which is often but not always applicable, something to consider, is the tail of the list x's is the result of a recursive call on some other input, of course generated somehow from Z. So your only question now is, what is the data that I should give to this recursive call? What is the seed from which I should grow the tail of the result? So if we go back to the sorting problem again, if you hit it instead with the structural co-recursion design recipe, you're led inexorably to a sorting algorithm, but not insertion sort, a different one, selection sort. So when does sorting produce the empty list? Of course, when the input is empty. If it produces a non-empty list, what is the head of the result? Well, that's the minimum of the input. And when it produces a non-empty list, the tail of the result is a result of a recursive call. From what data is that recursive call made? What is the seed from which we grow the tail of the sorted result? Well, that's the input data less the minimum element that you used for the head. So this is no more difficult, no more mysterious than insertion sort, as long as you realise that you can use the structure of the output data, another list, to determine the structure of your program. Now, how to design programs doesn't stop with structural recursion. It goes on to some more elaborate and sophisticated design recipes, and one of those is generative recursion. So this is a generalization of structural recursion. You make recursive calls on substructures, but the substructures are not immediately present in the problem. They're not obtained by projection from the input data, but by some more involved computation. You have to do some work to come up with the subproblems. So the design recipe for generative recursion says you've got a problem, you have a test for triviality. If it's trivial, you solve it by some other more basic means. Otherwise, you split it into subproblems, recursively solve those subproblems, and then combine those subresults into the overall result. Now, of course, this is a divide and conquer algorithm scheme, and students are being led by this design recipe to divide and conquer algorithms. But another way of looking at this pattern of computation is that it's about a structural recursion to grow a tree of subproblems, followed by a structural recursion to consume those results of those subproblems. So we start off with our initial problem, we break it down into smaller and smaller problems until we get to the leaves of a tree, which are trivial subproblems. We solve those, and then we can solve bigger and bigger subproblems until we get the overall solution. So it's a combination of the two patterns students will already have seen, structural recursion and structural co-recursion. The book is pretty apologetic about generative recursion. It describes it as an ad hoc activity, more ad hoc than the data-driven design of structurally recursive functions. Better to call it inventing an algorithm than designing one, because it requires insight, it requires a eureka step to figure out how to split the problem into subproblems. And then it goes on to say that we mere programmers can't be expected to come up with this kind of program. We have to leave that to cleverer mathematicians. But once they've had the idea, the insight, then we programmers can do the drudge work of implementing it. And I say that's too defeatist. I say that programmers can come up with this kind of solution. Now, I agree that it requires some insight, because the structure that determines the structure of the program is not there in your input data and it's not there in your output data. It's the structure in the middle instead. So yes, some insight, some eureka is required to come up with that. But from that point, there's no ad hocery. Everything is structured. There's a structured co-recursion followed by a structured recursion determined by your insight. So this actually reinforces the book's message that program structure follows data structure. The data structure in this case is something you have to invent. So that's my message. Program structure follows data structure. But we should not limit ourselves to considering input structure. We should consider the output structure too. If we have recursively structured data, that's likely to lead to recursively structured programs. But there might be structural recursion if they're over the input data, or structural co-recursion if they're over the output data. Once you've identified those two separate gadgets, structural recursion and structural co-recursion, you can put them together in new and interesting ways. And in particular, you can get divide and conquer algorithms by combining structural co-recursion and structural recursion. I've used Haskell as my vehicle for this talk, but none of this uses laziness. It all works perfectly well eagerly. Structural co-recursions will need some termination argument to demonstrate that they're producing finite data. But generative recursion in the book, How to Design Programs, needs this anyway. So this is not new material that needs to be covered in a course. It's already there. And of course, what I've said is not new. It's all there really in the work from the 1970s by Tony Hoare and Michael Jackson and Fred Brooks and many others. There's more discussion and there are more examples in my paper, How to Design Co-Programs, which is in Journal of Functional Programming. Thank you.
Hi, my name is Sandro, and today I'm going to talk to you about higher-order subtyping with type intervals. The talk is going to take us on a meta-theoretic journey, a bit of an odyssey actually, where we'll have to carefully navigate the challenges of different sorts of subtype systems, avoid the pitfalls of inconsistent bounds in the presence of subtyping reflection. It's the stuff of type-theoretic nightmares. So you may wonder, why should I care about higher-order subtyping with type intervals in the first place? To answer that, we'll have to go back a few years, to 2016. For the better part of 2 decades, Martin Odersky and his team had been working on solid theoretical foundations for the Scala language. And they were about to make a breakthrough with the dot calculus, a minimal core calculus for Scala's type system. Dot had already been in the making for a few years. But it wasn't until the end of 2015 that the proof of type safety really came together. Dot is a minimal core calculus. It doesn't have all the features of the full Scala language. The idea is that many of the surface features can be encoded into the minimal calculus, which makes the calculus itself easier to reason about and to prove properties of. One of the surface features of the Scala language is its rich hierarchy type language. It's basically a small functional programming language at the type level itself. And this is one of the bits that we were hoping could be encoded into the dot calculus without having to be in there from the beginning. Dot wasn't just a theoretical project. It was actually the foundation of a new compiler that Martin had been working on for a few years called Dotty, and that has now become the Scala 3 compiler. Dotty is a full-fledged Scala compiler, and so it really needs to support all of the features of Scala. And there's no such thing as a type safety proof for Dotty. But under the hood, it still uses a lot of the ideas of Dot. One of the problems, though, is that Dot didn't support the rich hierarchical language of types that Scala supports. But the hope was that these could be encoded in Dot. Unfortunately, that didn't turn out to work. So only a few months after the proof of type safety for Dot had been published, Martin and the other core developers of the Dotty team published an experience report where they outlined different ways in which they had tried to encode hierarchical types into Dot. None of them had worked. In the end, they were forced to add back hierarchical types into Dotty. And there was again a gap between theory and practice. In this paper, we address this gap and propose a rigorous theory of hierarchical types in Scala. Before we dive into the theoretical details, let's have a look at an example of how hierarchical types are used in practice. Here are 2 type definitions written in Scala. They're representative of the sort of code that you would find in a standard library. Don't worry about the complexity of this definition. It's very dense and you don't need to understand the details. We'll only use it to illustrate some of the advanced features of Scala's type language. The first thing to notice is that Scala types can take type parameters. They're so-called type operators. Now, Scala is not alone in this. Lots of languages have generic types that take type parameters. But in Scala, you can really write down type functions. For example, the first definition actually defines a type function in much the same way that you would define a term function. Scala methods can take type parameters too, just like functions in other functional programming languages. But Scala implements bounded polymorphism, meaning we can enforce constraints on type parameters in the form of lower and upper bounds. In this particular case, the type parameter C has to be a supertype of A and a subtype of B. And because types can take parameters, it's only natural that we would allow bounds on those as well. This is what is called a bounded type operator, and those are actually fairly exotic in the type theoretic literature. Okay. Let's have a closer look at what it actually means to put bounds on a type. Here is the general shape that a declaration of an abstract type X will take in Scala. It can have a lower bound A and an upper bound B. The idea is that whatever the type X turns out to be once it's instantiated, that type will have to have A as a subtype and B as a supertype. Another way of thinking about it is that X is an element of the set of types that are lower bounded by A and upper bounded by B, a sort of interval between A and B. Now, this intuition that there's a set of values that a certain expression can take sounds an awful lot like a type itself. or rather, because it's a set of type values, a kind. We formalize this idea in our type system f omega int through the notion of interval kinds. You should read the declaration x:(a.b) as x is of interval kind a to b, or in other words, x is contained in the interval between a and b. Now, there are other forms of type declarations in Scala, but they're really all special cases of this general template. For example, we can declare a type x that only has an upper bound b, but really that's just a type x contained in the interval where the lower bound is the bottom type. The bottom type is the minimal type, meaning every other type is a supertype of it. And similarly, if x is only declared with the lower bound, that's the same as saying x has this degenerate interval kind that is upper bounded by the top type, the maximum type. Every type is a subtype of top. If a type is declared without any bounds at all, it's just a member of the degenerate interval that goes all the way from bottom to top. We call that interval star, which is the usual notation for the kind of all types. And conversely, if a type is just an alias of another type, then that's the same as saying that it's contained in the interval that is upper bounded and lower bounded by the same type A. This is called a singleton interval or just a singleton kind. What I've shown you so far could really have been expressed in Dot already. What's new in f omega int is that we also represent type operators explicitly. So here's the general template of a type operator with one parameter. As before, we can declare bounds on f itself, or in this case on its body, but we can also declare bounds on its parameter x. This is a bounded operator. In f omega int, such declarations are represented using dependent function kinds. They take types from one interval to another. Here are some examples. First, we can encode aliases of type operators in much the same way that we encoded aliases of proper types. For example, here we have an alias of the type constructor list. It takes a type parameter x and returns an element of the singleton kind that contains just lists of x. Often, we don't want to define aliases. We want to declare abstract type operators with certain bounds. For example, here, the abstract type operator f2 of x is upper bounded by list of x, which means we can instantiate it with a subtype of list of x. For example, a linked list implementation or an array list implementation. Of course, that's not the end of it. F omega int has a rich, higher order type and kind language. So we can encode type operators that have multiple parameters by occurring, that have parameters that are themselves operators, and we can even have type parameters that are bounded operators. Note that in all three type declarations, the codomain of the function kind actually depends on the parameter x. So dependent kinding really is used here. And again, these declarations are fairly representative of what you would find in a Scala standard library, for example, in the collections framework. Now that we have an idea of how bounded operators are represented in f omega int using type intervals, let us take a tour of the main result of our paper, namely the type safety of f omega int. And let's have a look at the challenges involved. As usual, for a system that involves subtyping, the main difficulty to proving type safety of f omega int is to prove subtyping inversion. If we're given two arrow types that are related, then we should be able to infer that their domains and codomains are also related, and similarly for universal quantifiers. The proof of subtyping inversion in f omega int is complicated by the fact that we have type-level computation, but also dependent kinding. One of the main challenges when inverting subtyping in a system with type computation is that in the middle of a subtyping derivation, we may encounter a beta reduction or an eta expansion. Because our system has subkinding, there's a similar problem with subsumption, which can also appear anywhere in a subtyping derivation and thus block simple structural inversion. And finally, we actually have a form of subtyping reflection in f omega int, and this will destroy all the nice structural properties of the subtyping judgment. I won't go into the details of the second challenge in this presentation, but let's have a look at challenge number 1 and 3 a little bit closer. The standard declarative subtyping judgment of f omega int is a bit of a monster. Besides the usual structural rules for subtyping, it also contains computation rules. And these rules can get in the way of a structural inversion. You can see this in the example judgment on this slide. On the left-hand side, there is an arrow type. Then we perform a beta expansion, so we get a type application. Then there are some intermediate steps that don't really matter. We get an application again, we beta reduce it, and we end up with an arrow type as well. But there's no telling whether and how these two arrow types are structurally related, going through all of these computations. We tame this monster by getting rid of radixes. We introduce a new canonical representation of subtyping where all type expressions are in normal form, and so there are no radixes and no reductions. But this introduces a new challenge, because the canonical subtyping judgment requires that everything is in normal form, including kinds. And because we're in a dependently kinded system, kinding involves substitutions, and substitutions don't preserve normal forms. So consider what happens if we're trying to type the following application. We have a type operator that's abstract, it's just a type variable, and we want to apply it to another type that is in normal form. The kind of the resulting application is the codomain K with the normal form V substituted for X. Even if K was a normal form, the resulting kind expression with the substitution doesn't need to be. We solved this particular problem by using something called hereditary substitution for the canonical judgment. Unlike ordinary substitutions, hereditary substitutions beta reduce and eta expand their results. You can find the details in the paper. The third challenge is of a somewhat different nature. Like dot, f omega int features a form of subtyping reflection. Programmers can introduce custom subtyping rules into the subtyping judgment via type intervals. This is a really powerful type system feature, and it can be used for good, but it also has a dark side, because we can reflect inconsistent subtyping rules into the subtyping judgment and break type safety. Let's have a look at an example to see how this works. Let's assume I've declared an abstract type X with the following bounds in my program. The lower bound is the type top, and the upper bound is the type bottom. These bounds are absurd, because of course the top type is not a subtype of the bottom type, it's the other way around. But hey, it's a declaration, and we can declare any bounds we want. Now because top is a lower bound of X, we can derive that it's also a subtype of X. And because top is a supertype of every other type, any type whatsoever by transitivity is a subtype of X. But X also has bottom as an upper bound, which means that X is a subtype of bottom. And because bottom is a subtype of every other type, any type whatsoever is a supertype of X. And so by transitivity, any type is a subtype of any other type we want. The subtyping relation becomes trivial, and we can relate types with completely different type constructors. So inversion is never going to work. This is not the only bad news, I'm afraid. Reflection of inconsistent bounds really breaks a lot of things. For example, subject reduction or preservation of types under reduction doesn't hold in general, and subtyping becomes undecidable, which we prove in the paper. The solution to this problem is basically to ignore it. We're just not going to attempt to prove subtyping inversion under inconsistent bounds. In fact, we're only going to prove subtyping inversion in the empty context. That's really all we need to prove type safety. If you like what you saw, there's a lot more in the paper. And finally, we have mechanized the entire meta theory in Agda, and the source code is available as an artifact from Xanadu. That's it for me. Thanks for staying with me until the end. And I also want to thank Paolo, my co-author, and all my colleagues that made this paper possible. Cheers.
Hi, my name is Sam Caldwell, and I'm here to talk to you about typed dataspace actors. The goal of this talk is to answer two questions. First, what is the dataspace model? And second, what extensions to the simply typed lambda calculus are needed for typed dataspace programming? So concurrent programming is hard. There are many ways to structure concurrent programs, so we've seen almost as many linguistic models arise, each with their own pluses and minuses. One particularly helpful idea is the isolation between components in the actor model. Unfortunately, isolation is in tension with another central need of concurrency, sharing knowledge. On the other hand, tuple spaces offer a view of knowledge in a concurrent system that lends itself to easier sharing. The dataspace model seeks to build upon these ideas and alleviate the tension between isolation of components and their need to share knowledge. So, what is the dataspace model? From 5,000 feet, it connects actors via a restricted tuple-space-style shared memory. The restrictions serve to decouple components and implement a publish-subscribe communication pattern for routing messages, but it's really best illustrated with an example. I'm going to imagine setting up a smart home lighting system in my apartment. Here I am with the components I need: a central control hub, networked lights, and presence sensors. The first thing I do is plug in the controller, which has a dataspace program running inside it. Here's a graphical depiction of that program. At the moment, there's a single actor representing the control system itself. I then start installing the lights. I've labeled the first L1. When I install a light, the system spawns an actor representing that light. That actor shares one piece of information in the dataspace announcing its presence. This takes the form of a tuple with the label light and an ID. We call these shared facts in dataspaces assertions because of their resemblance to logic programming. The hub actor uses these assertions for configuration and control purposes. For example, each time I install a new light, the system may prompt me to associate that light with a specific room. In order to facilitate this process, the hub actor subscribes to light presence information, which we see here. Now the way to read this is question mark, meaning I am interested in assertions matching the following pattern. The pattern matches tuples with the label light and any value in the second slot, signified by star. With the subscription in place, the system will inform the hub actor of matching assertions. Each light I install after that makes a similar assertion. In order to control each light, the hub actor asserts a control signal. Here it asserts that the control state for the light with identifier L1 should be off. Of course, in order to receive the control signal, the light actor needs its own subscription. It does so with an assertion of interest in controls matching its own identifier and any value. Another important element of dataspaces is the link between assertions and actors. If L1 burns out, for example, the corresponding actor will exit. When an actor exits for any reason, the system automatically removes each of its assertions. The hub actor's interest also subscribes it to these disappearances, yielding a corresponding routing event. This information allows the hub actor to withdraw its control for L1 and notify me to replace the bulb. Next, I install each presence sensor. I've labeled the first PS1. Like the lights, the system spawns an actor for each sensor. The actors make an assertion with a current sensor reading using the label present and their own identifier. The hub actor expresses interest in the reading of each sensor with a corresponding assertion. Now, to see how the program evolves, we tune in for a breaking update as I move from the couch to the kitchen for a snack. As a result, the present sensor, PS1, updates its assertion from 0 to 1. The update represents a change to the set of assertions matching the hub's interests. This is the condition for the generation of an event in a dataspace. The routing mechanism sends a representation of this change to the hub actor, bringing us to the subject of how the hub actor processes such events. To this point, I've been talking about dataspaces as configurations of actors, but ignoring the internal behavior of such actors. The dataspace models each actor as a pure function, so we can think of them as just terms in a lambda calculus. The signature for each actor is a function consuming information on updates to assertions that match its subscriptions and producing instructions to be interpreted by the system. These instructions pertain to manipulating the actor's own assertions, spawning other actors, or terminating. In this case, the hub actor will produce an instruction manipulating its assertions, namely changing the control signal for L1 from off to on. In turn, this update is relevant to L1's interest in control signals, yielding another event. This is the typical pattern of communication for dataspace actors. And here we see the light now on. Up to now, everything has been going as planned. But let's imagine a different reality where, while developing my control software, I get mixed up by all the different ways of controlling a light. On-off states, brightness percentages, HSV, RGB, and many others. While programming the hub, I represent lights as being either off or at some percentage of maximum brightness. But while programming the light bulb actors, I use just on-off states. Now, when the hub actor tells L1 to turn on, it does so with a percentage. This percentage still matches L1's interest, once again generating a routing event. However, now when L1 processes the update, it encounters a type mismatch, with the potential of causing any number of unexpected or undesired behaviors. Well, where I'm from, we don't like runtime type errors. To prevent them, we could develop actors using a typed language. We would then also have the potential for type-based design, documentation, optimization, and so on. So what would a typed programming language for dataspace actors look like? Recall that dataspace actors are pure functions, letting us model them as terms in the lambda calculus. It's then natural to use the simply typed lambda calculus as a starting point for writing typed actors. The informal signatures for actors can then be modeled as an arrow type. This leaves us with needing to determine what extensions to SDLC and arrow types we need to reason about dataspace events, instructions, and actors. Let's go back to our example to illustrate how to design types to meet these goals. Here's the point where the hub actor controls L1 with a brightness percentage rather than an on-off flag, introducing a runtime type error. A type system must prevent this scenario from occurring. At the same time, it ought to allow instructions that update the control assertion using on-off flags. This situation calls for suitably fine-grained types to distinguish the two scenarios. This is our first extension to the simply typed lambda calculus, a reflection of the assertion language to the type level, allowing for precise descriptions of assertions. Types include the constructor for assertions of interest, the question mark, the star pattern, and tags such as light, control, and present. Using this type language, we can enumerate the different assertions the hub actor manipulates: interest in lights, on-off control signals, and interest in present sensor data. These form the basis of the instructions type for the hub actor. They also need to be combined in some way. True union types are convenient for this purpose and are the second extension to the simply typed lambda calculus we use to describe dataspace actors. Now, going back to the example, we can identify the types of assertions produced by each actor in the system. We see that the light actor L1 produces light ID assertions and subscribes to control signals, and similarly, PS1 shares its presence reading. Moreover, if we take the union of each of these, we get a picture of the types of assertions across our whole program. From this view, we can easily conclude that all light control assertions are in terms of on-off states rather than brightness percentages. So we now have a reasonable way to describe the instructions for each actor, but what about the events? Since events are also descriptions of assertions, it follows that their types are then going to look similar, meaning unions of assertion types. And recall that the hub actor is a typed lambda. When I write the term, I am free to assume a type of my choosing for the input, and then program the rest of the behavior according to that type. The responsibility of the type system then lies in ensuring my assumption is valid in the context of the larger program. To understand how this plays out, let's look again to our example. Here we are back at the moment when the hub actor processes a presence update event. Earlier, we saw the generation of this presence update event was due to a change in PS1's reading and a matching interest from the hub actor. At the type level, we recognize a similar match between the hub's type of interest and presence readings and the type of sensor data assertions. We can then conclude that such assertions are potential events for the hub actor. Looking back at the types, we notice another match for light assertions, so they are also potential events for the hub actor. The pattern here is the following rule. If an actor may express interest in a type of assertion, then its type of events must include any assertion that may match this interest. This process directly corresponds to the routing procedure performed at runtime in dataspaces. To generalize beyond this example, I'm going to replace each concrete type with a metavariable. Our system checks each actor by first analyzing the instructions type for question mark prefix assertions, i.e. interests. We then cross-reference those interests with the type of all potential assertions in the dataspace, determining the types of potential matches. Finally, we ensure that the domain of the behavior function corresponds to this type. This loop of dependencies is our final addition to the simply typed lambda calculus. Fundamentally, this extension adds an understanding of how data moves between actors and dataspaces to the type system. Here's a simplified type rule implementing this reasoning. To check an instruction that spawns an actor with a given behavior, we first ensure that behavior has an arrow type. The codomain of this arrow type is the type of instructions the actor may produce. From these instructions, we extract the pattern from every type representing an assertion of interest. Finally, we cross-reference these patterns with a provided type representing the entire dataspace to find all potential matches. These matching types are potential events for the actor, so must be included in the domain type of the arrow. Now to recap what we've seen, the dataspace model of concurrency seeks to tackle the tension between isolation of concurrent components and sharing knowledge among them using tuple space-inspired publish-subscribe communications. To extend the simply typed lambda calculus with types that allow us to capture the structure of database communication, we can first reflect the assertion language at the type level, second, combine different possible communications with unions, and third, perform type-level routing to understand which communications are possible. There are many things included in the paper that I didn't cover in this talk, such as our prototype implementation using the turnstile DSL, a discussion of the value of termination for dataspace actors, and a thorough semantics. The semantics allows typed STLC components to interoperate through an untyped substrate, the dataspace. We combine these untyped concurrent and typed sequential models and improve the soundness of this composition. You can find the paper from JFP Volume 30, August of 2020, and at the given link. Looking beyond this paper, the dataspace model is implemented as Syndicate, including extensions and libraries to several languages such as Racket and JavaScript. Our turnstile prototype adds types to Syndicate and Racket, while we are exploring designs for Syndicate and TypeScript that account for dataspace communications. Now, rather than program dataspace actors in the lambda calculus, we use a DSL oriented around assertion-based conversations. This opens the possibility for richer type structures. When we model actor behaviors as arrow types, we lose information about the relationships between assertions. Looking back at this diagram describing the hub actor, we analyze the entire right and left-hand sides of the arrow at once. Doing so loses track of the fact that it is interest in light assertions that leads to light events, and interest in presence data that yields presence events that in turn leads to control updates. Tracking these temporal relationships is the basis of ongoing work on behavioral types for dataspace actors. Thank you very much and stay tuned.
Thanks so much for tuning in to this talk about collaborative research on existential types. Before we get into the details of what we're doing with existentials here, I want to motivate a little bit about why existential types might be useful. So this first example is I call it an object encoding. It's a way of mocking up object-oriented types in a strongly typed functional programming language like Haskell. The idea here is that we can have a show-all function that takes a list of this existential type. So here, each element in the list has some type A. Each A can be different, but each one has to have a show A instance. In other words, each one can be rendered out to a string. Then the body of show-all can show each element individually and concatenate all the results together. Then I can use show-all on what appears to be a heterogeneous list. This 3, true, and x, it's not really heterogeneous because actually each one of these has this existential type because each one of these has a show instance. Another example. Let's say we want a richly typed data structure. So here we can imagine a data type well-typed expr, which holds abstract syntax trees for some little programming language, and we want 1 plus 2 to be a valid well-typed expr, but not 1 plus bool. In order to describe such a thing, we need to actually index the data structure with the type so that the representation for true would be known to have type bool, and the representation for 1 would be known to have type int. Then, in a larger compiler, we might have a parsed expression, which is as yet unchecked, this unchecked expr, and we want to check it to form a well-typed expr. Of course, we don't know what type it's going to have until we actually check it. And so this checking this is going to produce an existential type because I don't know what tie is going to be. So here, once again, we need an existential type. Another related application is that maybe I already have my richly typed structure, but I want to perform some operation on it that means I can't really preserve my knowledge of that's encoded in the types. So if I have length indexed vectors here, n, and then later m, this is the length of a list essentially, right? I want to be able to filter that list. Well, I don't know what the output is going to be based on the input. I know this output length m has to be less than or equal to n, but that's a pretty vague relationship, right? And so I can't say compute the result of m just based on n. So that means that there's going to be some length of my output vector, but I don't know what it's going to be. In other words, it's going to be existentially bound. There exists a length m, but I don't know what it is. The goal of this research is to make existentials as easy to use as universals. So basing ourselves on Hindley-Milner type inference, right, we get universals essentially for free. We get let generalization that peppers our code with universal quantification, and we get to specialize our polymorphic functions whenever we need to. I want existentials to be, well, almost as easy. Unlike with universals, where all of the universal quantification is totally inferred, we're going to write the existential types in. We're not going to do some automatic equivalent of let generalizations or corresponding idea to let generalization to get our existentials. Instead, we'll write them in, but we're not going to write places where we create or eliminate existentials in terms. So let's dive into the filter example because we can understand more about the specific design that we're advocating here in this work. So we start out with our usual unary natural numbers as well as our usual length indexed vectors. Nothing surprising here. And then we can define this filter. So this is the same filter type that we saw a few slides ago, but now we have an implementation. What we see in the implementation is that there is no packing or unpacking, despite the fact that this filter returns an existential. The first line just returns nil. I don't do any fancy footwork there. And then the recursive call to filter, again, I don't have to use any fancy footwork. The approach that we describe in our paper accepts this definition. Let's look at it a little bit more closely. The first observation I want to start here, and sort of the key thing that drives part of our design, is that filters should be lazy. The idea here is that in a lazy language, I might want to look at the result of filtering before I've finished actually computing the filter on all of the elements in a list. Right? If I have a list of 100 elements and I'm doing some filter, maybe I only need the first 2 results and I won't need any of the rest. If that's the case, I don't want to have to do the work of filtering all the rest of the elements. That means that filters should be lazy. One requirement for a lazy filter is that I can't pre-compute this recursive call. In this px line, right, if this predicate p, if that holds, I need to make this recursive call to filter. I don't want to make that recursive call until I've already set up the cons operator. But this cons operator, right, this cons operator takes a vector of length n and gives us back a vector of length suc n. So it actually takes, at compile time, it takes the length of the tail. We might imagine taking our nice surface language that doesn't have any packing or unpacking and desugaring it into a core language that does have packing and unpacking. So we might imagine taking the code that we have toward the top of this slide and getting the code that we have toward the bottom. On the bottom here, we have this unpack. This is based on ideas from Mitchell and Plotkin from their Popple 1985 paper. We can have unpack, which we would run on this recursive call to filter. That produces this, it's not written in the code here, but that will sort of extract out the length of this, this recursive call, the length of that filtered vector, x is prime, and then it would make that length available for use in the call to cons. This works, but this destroys our laziness. For this to work, we need to actually evaluate this recursive call before cons. That's no good. This is not lazy enough. So if filter is going to be lazy, and yet cons needs to know the length of the vector's tail, then we want to get that length, we want that not to require any evaluation. After all, that length is just a compile time value. There's no reason we need it at runtime. We shouldn't have to affect our runtime evaluation in order to satisfy a compile time requirement. That's a bit backwards. Let's look, there's one more desiderata that we want to consider in our design. And that is, here I have a hidden int, right? There's the idea is that we have some type A, we don't know what it is, but we can project out an int from it. We can create such a thing using this function mook. So in my result here, I'm going to say hidden is mook true. So we create one of these hidden ints, and then I project out the int inside by using the second element of this tuple and applying that to the first element. I want this program to be accepted, right? There's no trouble here. And this turns out to be relatively easy. I can compile let into unpack, right? I can use let and say, okay, let's just take this existential, we'll make this A available inside the scope of the let. But now, suppose I want to rewrite my program by doing a little let inlining. Right? Instead of saying let hidden equals mic true, I just want to repeat mic true twice where I previously wrote hidden. That should still be accepted. I should be able to inline my lets. Yet now the unpack is much harder. It looks like I would need to insert the unpack surrounding this whole result, which now is going to affect my runtime evaluation again. So this is problematic. The key idea that unlocks the design that we want is to not use unpack, but use another construct called open. The idea here is if I have an expression E of existential type, then open E is just the inner type, this type tau, where this type variable A is replaced with the existential projection of E. Right? We can almost view an existential type as a dependent pair, where there's a type as well as a term that depends on that type. So here, these funny brackets, this existential projection is like calling first of that dependent pair. Open is like second of that dependent pair. This is not a new idea. McQueen in 1986 called this witness and out instead of my funny brackets and open. And using this open construct sort of unlocks everything else that we need in order to get these lightweight existentials. So using open, existentials can now be opened anywhere. I don't have to think about an unpack which then limits the scope of my existential variable. I can just call open whenever I need to. This is really important if we're going to avoid affecting runtime evaluation. Working with an existential projection of E does not require evaluation. This step is really important, and purity is a key part of the recipe here. In that, if let's say every time I evaluated some expression E is an arbitrary expression, it does not have to be a value. If every time I evaluated E, I might get different results, well, then we're carrying around this existential projection of E in types where it might be duplicated. Well, that would no longer be sound. So purity is very, very important. Pack and open. I haven't mentioned pack. Pack is the way that we create existentials, and it's quite standard. Pack and open are erasable for runtime here. So that, again, means we don't change our runtime evaluation in order to satisfy compile time properties. There is a challenge here in that expressions E can appear in types. Because of this challenge, we need to now define what it means for expressions to be equivalent when we're doing type equality. So for now, we can just use alpha equivalence. It turns out a richer notion of equality on expressions, to use, say, full beta equivalence, is fully compatible with our ideas, but we don't need that. So for now, we'll just stick with alpha equivalence. So we've taken this idea from 1986. Why now? Why can we suddenly do this now and we couldn't do it beforehand? So there's a couple of key ingredients that all mix together very nicely. One is the setting in Haskell. Haskell gives us purity, and as we've seen, that's really important to be able to talk about these expressions that suddenly live in types and might get duplicated. We have laziness, which helps to motivate why this approach is a good idea. With these expressions in types, that's kind of like dependent types. So because we are more comfortable with dependent types, symbolized by this capital Pi here, it means that we understand better how expressions in types might work. Back in 1986, this was very, very strange, and even then, we're like, McQueen was unsure of the wisdom of this approach. In the other ingredient right now is that to make a type inference algorithm that works well, it's really nice to base it on the quick look algorithm that came from last year's ICFP. That gives us a structure by which we can easily understand how we can do inference for existential. So all of these ingredients combine quite nicely. So I've talked a lot about the motivation and some user-facing features. What's the technical meat? So in the paper, there's a type inference algorithm based heavily on quick look that elaborates into a core language built with open that is type safe. This algorithm in this language has some nice properties. So if the inference algorithm succeeds, we're guaranteed that the elaborated program is well typed and that it retains the semantics of the original program if we just erase all of our types. This algorithm is a conservative extension of Hindley-Milner, meaning all of our old programs continue to type check. It's a bidirectional algorithm, and when we infer a type, that same type can be used in checking mode. This means we can add annotations without affecting typability. We also have some nice properties that we can refactor our programs, reordering existential quantification and doing let inlining without disrupting typability. Interestingly, none of this was very hard to prove. The conclusion here is that by using open in our core language, we can have all these nice things. Thanks very much for watching.
Hello, I'm Andrew Flinsky, and I'll be talking about matching regular expressions with functional programs. This talk is based on an article in JFP on the occasion of Bob Harper's 60th birthday, which I guess is a couple of years ago by now, but he has even round one coming up, so it should be okay. I'm particularly happy to present it at ICFP because there was a conference that Bob helped start. We're looking at a rather simple problem, just deciding whether a string belongs to the language denoted by a regular expression. And we actually already know how to do this efficiently, thanks in large part to a number of people who also made significant contributions to programming languages, not just formal languages. But what I want to do in this talk is to hopefully convince you that a number of these classic automata theoretic constructions can actually be seen as instances of general transformations that we know in this community, and in particular that we can then prove their correctness by just reasoning about the meanings of pure functional programs. Okay, so this is what we start with, a continuation-based backtracking matcher that's essentially the same as the one in Bob's proof-directed debugging article. So the main matching engine takes a regular expression, a continuation, a string, and then tries to match the regular expression at the beginning of the string, and if it succeeds, it calls the continuation on whatever's left of the string. And if there are multiple ways of doing that, it's enough that only one of them succeeds. So, for example, when the regular expression is a single character C, we check that the string in fact starts with that character and call the continuation on the remainder. And down here in the most complicated case, when the expression is star R0, we can either succeed immediately by calling the continuation on the entire string, meaning that we did 0 iterations of the star, or we can do at least 1 iteration at R0, and then on whatever is left, we do again another R0 star. And then the initial continuation just checks that we've consumed all the characters of the original string. So this code works to some extent, but it has two significant problems. One is that down here in the star R0 case, if R0 can match the empty string, for example, if it's epsilon, then the S prime here will actually be the same as the S in the original call. And that means that in this inner recursive call, all three arguments will be exactly the same as what we started with. And of course, that'll not end well. And secondly, it actually has pretty awful performance. It's exponential both in the size of the regular expression and in the length of the string. That's for a rather silly regular expression family, but even for ones that you actually want to match, the performance can in general be exponential in the length of the string, which is not good. Okay, so let's start with divergence. And in fact, we can use the original matcher if we just work around its limitations. And we can do that by pre-processing the regular expression so that all star bodies are made non-nullable. There's a syntactic transform for that. And that will not change the language of the start expression, but it will avoid the problematic case in the matcher. Unfortunately, the details are somewhat involved, and especially the size of the regular expression may blow up. So if we care about performance, that's probably not the way we want to go. But a rather simple solution is to just dynamically do the same thing. That is, after matching the first R0 here, we just check whether the string that's left actually has gotten shorter than what we started with, and if not, then we give up. And that works great, but unfortunately, it's going to upset some of the transforms we want to do later, so we cannot use that either. But we can do something very similar. We'll just keep a separate Boolean flag that tracks whether the state got whether the string got shorter since we started the star body. And then whenever we actually consume a character, like in this case, we set the flag to true. And then when we start matching a star body, we set it to false. And then check, and if it's still false by the time we've finished matching R0, then we give up. And doesn't actually matter what we initialize it to. So that way, there's only going to be finitely many continuations for any regular expression. Okay, so now we want to argue that the final match is actually correct. And that boils down to three things, that for all input expressions and strings, it actually returns an answer. And if that answer is true, then the string did belong to the language of the expression. And conversely, if the string did belong, then the answer will be true and not false. And all of these can be proven by induction in various ways. We have to formulate a suitable induction hypothesis for the match engine itself. We take a little bit of work, but after that, it's just doing the obvious thing. So now let's look at performance. And here we note that we never actually construct the new regular expressions at runtime. They're all just sub-expressions of the original top-level one. And that means that it's actually feasible to specialize the matcher to a given regular expression. That is, instead of performing the matching actions directly, we generate code that will then do them once B and S become known. So if we, for example, look at this regular expression that matches strings of A's and B's that start with an A and then a B, and I just throw in this bar epsilon in the middle to make the loop detection work a little bit harder, then this is the code we get. So this is just a fixed utility combinator that checks that the current character is C and skips over it. and then the expression actually gets translated to these mutually recursive continuations. K5 is the main continuation, the one we begin with, and that checks, well, is the first character in A, and if so, continue with K4. And here we have the choice, so we can either do 0 iteration of the loop body, which means we go straight to K1, which expects the B, this one, and then we better be at the end in K0, or we could do at least one iteration of the loop body. So we do that in K3, setting the flag to false, and K3 is then this three-way choice for the loop body, and they all end up in K2. And K2 checks that we actually did consume something, and if we did, we get another choice. Do we want to exit the loop now, or do we want to do another iteration? And then we just start it off down here. So in practice, we don't actually generate ML code. We generate code for a little abstract machine with combinators expect, at end, and so on, corresponding to the actions that we do at runtime. And if we want to, we can then run that with a little interpreter. So unfortunately, specialization by itself is not going to improve performance significantly, and in particular, it's not going to help with the asymptotics. But if we actually look at the code, we see there's a lot of recomputation going on. We keep invoking the same continuations on the same string. So what we're going to do is to use dynamic programming and proactively apply all continuations to all suffixes of the input string and all input flags, regardless of whether we think we'll need them or not. So we're going to do this by putting together all of the continuation results for a given string, and we compute them starting with the empty string, conceptually at the end. We just find the values or the results of the continuations, and then it turns out that we can find the results for a longer string as a function of the results of the tail of the string and the character C prime itself. So we can process the string from the end and keep extending this tuple. And if we do that, we end up with this code. So the step function takes the next character, or none if we are at the very end of the string, and the results from the previous step. And then it checks, well, are we at the end of the string or not? And here we just have two copies of what we had previously, just slightly abbreviated, but where we compute the values for the flag being false first, and then for the flag being true. And the main difference is actually that when the flag is false, then this B and also just immediately gives us false, whereas down here there's something to compute. And this is what actually avoids the circularity, because we are referencing F3 here, even though we are in the second continuation. And that way we get the result tuple. So our traversal function just starts at the end of the string with some dummy value, and then keeps applying the step function until we get the tuple of final results. And then we just extract the results for the last continuation, which tells us whether we should accept. Okay, so now we have a deterministic matcher that actually runs in reasonable time. And to show it correct, we just have to show the property from the previous slide. That is, that run indeed in one go computes the result of all the 6 continuations as if they were tupled up. And once we have that, well, we are essentially done. So for the next step, it's helpful to look at what does this step function actually compute in the two cases. So when we call it the none, which means we are at the end, we return this tuple where the continuation that checks whether we are at the end returns true, and everything else returns false. And when we're in the middle of the string, the next tuple depends on the previous tuple and the character we're looking at right now. And turns out when that character is A, well, we're computing this function of the old results or previous results. And when the character is B, we compute this function with some ors in it. And if it's any other character, all the continuations return false. So we have this all false tuple, and we're still extracting the A5 bit. So we can write this as a folder and compute what we expect. So I should say that in practice, we don't want to actually fully expand the definition of step into init and next, because even though it looks simpler in this example, in general, these OR computation can get quite heavy. And if we just expand them out, we lose all the sharing. And so this can actually take quadratic time in the worst case, rather than just linear time in the size of the original expression. So we want to keep it intentional. The other oddity is that we are processing the string from right to left, but we can change that. If we want to use for left, we just have to reverse the string first. Or alternatively, if it's not practical to reverse the string, we can reverse the regular expression. It just means swapping the arguments of seek, and we can do that while we're translating. And that way we get a string processed from left to right. And when we reach the end, we can immediately say, should we accept it or not? Okay, so we have a state machine, but the states are kind of big, and computing the next state actually takes some time. So we'll want to pre-compute that. In fact, we only have to do that for the states that are reachable, not all of them, so that may be just a fraction. We do that by assigning a state number to all the reachable bit vectors, and state number 0 is going to be the dead state, the all false one, and that on any character just steps to itself. State number 1, that's the initial state with true here and false everywhere else. And if we apply the next function to that, if the character is A, we actually end up in the all false state. So that's already covered by this catch-all. But if we apply the function with a B, then we go to the state FTTTF. And we haven't seen that before, so we call that number 2. And there's a case for that. And so we keep on doing this until we see no new state. And then we're done. We also extract the value of the last continuation. That's the one we're interested in. And then to actually run this machine on a given input string, we just traverse it again with full R. And at every character, we look up the map here, apply it, and keep on doing this. And at the end, we observe the result, which is just the first component. So to do this in practice, we have a little try that keeps track of all the vectors we've seen. And that means that we can actually do this transformation in time proportional to the number of reachable states times the size of the regular expression. And we don't actually generate functional code here. These are all first-order data structures. And of course, we also want to prove it correct. And it turns out that the try that we used to do the conversion is actually precisely a witness that the new machine simulates the old one. And once we have that, again, we can rely on the previous machine being correct. Okay, so unfortunately, I'll not have time to talk about state minimization at all. I just wanted to point out there is actually a nice story to be told. And in particular, this means that with just a few more lines of code added, we can not only check whether a string belongs to a language, but we can actually decide whether two regular expressions denote the same language, or maybe whether one is a subset of the other. Okay, so we've seen how to get from a slow and buggy matcher to a fast and correct one. This should be a self-contained development, but if you look at the constructions the right way, you can actually see something very analogous to a lot of these classical constructions, NFAs, epsilon closure, and so on, slightly differently, but doing essentially the same thing. So you can see the full code for everything in the article. No libraries needed. It's a little bit more complicated than the example-based presentation in this talk, but not a whole lot. And I should probably also mention that, in fact, all of the proofs have been machine checked in the 12 framework, which means very little automation. And in that framework, the proofs are about 4 times the size of the executable content when that's recoded in 12. But with some automation, this would probably be brought down significantly. Okay, so what else can we do? Well, there are probably a lot of other algorithmic results that can actually be seen as instances of applying general purpose transformations to a less efficient program for achieving the same task. So exploring that should certainly be educational. But I guess the real test is not only can we recover old algorithms, but can we develop new ones in areas that perhaps haven't been so well studied as regular expression matching. And in fact, even in the matching domain, there are a lot of variations and parameters to tweak. So we may vary what are we computing, just a bit or an actual pass. Which setting are we doing it in? Maybe it's not exactly a regular expression. Maybe it's 3 automata or whatever we have. Maybe we care about how we compute it, for example, in parallel. And most especially, it would be nice to get some more automation of the transformations so that we can get the computer to do the specialization, for example, rather than doing it by hand and then proving it equivalent separately. But I think we can all agree that regardless of whether we actually end up coding the solution in a functional language, it certainly helps to think about it in that way. Thank you.
Hello everyone, this is Xuejing from the University of Hong Kong. Today I'll present a joint work with my supervisor Bruno, distributing intersection and union types with splits and duality, functional pair. In this work, we design a novel algorithm for subtyping, with intersection and union types and some non-trivial distributivity rules. The subtyping relation is based on a logic system called B+, and our approach is a combination of two recent ideas, splitable types and dual typing. Splitable types are types that decompose into two simpler types, while dual typing is a generalization of subtyping. We have a compact Haskell implementation and a COQ formalization containing all the proofs. So the story begins from the B+ logic. It is a minimal positive relevant logic system invented in 1972. PL researchers then discovered that such logic system can be used to guide the design of type assignment systems with intersection and union types, and its axioms can be interpreted as subtyping rules. So, what are intersection and union types? Given type A and B, any term of A intersection B contains the information of both A and B, while a term of A union B only needs to have the information of either type A or type B. That is similar to logic conjunction and disjunction. And we know that logic reasons on propositions. Following the Curry-Howard polymorphism, propositions correspond to types, implementations correspond to function types. Conjunction and disjunctions then correspond to intersection and union types. But to translate a logic axiom, which itself is a proposition, the top-level implementation has to be converted into subtyping. So here, as we can see, A implies disjunction of A and B is translated into A is less than A union B. And in logic, we ask if a statement follows from another statement, while in subtyping, we ask if a type is a subtype of the other one that are quite similar. So here we show some basic subtyping rules for intersection and union types. The S and L rule and the S and R rule say that the intersection of two types is a subtype of each component. And the rule Sn states that any common subtype of B1 and B2 is subtype of B1 intersection B2. In the reverse, for the union type, if A1 is a subtype of B, which means B is a supertype of A1, and B is also a supertype of A2, then it is a supertype of A1 union A2, which itself is a supertype of A1 and A2. And now, intersection and union types, they are commonly seen in programming languages like Seduce, a language for XML processing, Scala, and also the upcoming Scala 3 that is based on the dot calculus, or the language Julia. The most challenging part in the subtyping relation around the intersection and the union types is the distributivity rules. In the first one we show here, it distributes intersections over functions. And the rule is also in the BCD subtyping. In the second rule, intersection and union types distribute over each other. Note that in both rules, if we flip the direction, in the other direction, the subtyping judgment is also derivable in the subtyping relation. So the two pairs are actually the two types are actually equivalent. For example, given two functions that both take an integer, where the first subtyping rule, we can treat them as a single function. which pass the input to both the successor function and the int2string function. And then it can combine the two results, which has type int in the section string. And if we already have such a function from type int to int in the section string, we can use it as a function of either int to int or int to string. That's the other direction. On the other hand, to get some intuition behind the second rule, we can consider all the possibility we get from the subtype, the intersection of A1 union B and A2 union B. We either get both A1 and A2, or we get type B. So we say that it is a subtype of A1 intersection A2 union B. Actually, there have been many algorithms around this topic, but most of them rely on a normalization phrase, while our algorithm directly works on the source type. Take the integrated subtyping framework developed by Milbach and Tet, for example. To decide if type A is less than type B, it firstly converts A into a disjunctive normal form, and then transforms each conjunction part in the DNF to do further checking. And some algorithms formulations of the BCD subtyping do not need such a process, but they don't support union types. In both Pierce's decision procedure and the sixth subtyping system, the domain and the codomain of a function type are separated for comparison. Now, let's take a closer look for our subtyping formulation. Remember, it used two ideas, type splits, that we use it to deal with the distributivity rules, and dual typing. It provides another viewpoint for us to unify the system. I'll show them one by one, so we'll start from the splits. The idea of type splits was proposed to design an algorithm for BCD subtyping, which does not have union types. In this problem, the key challenge is to deal with the additional distributivity rule on the top of a simple subtyping relation around the intersection types. Conventionally, types like int or top that are not intersections are called ordinary types. So any function types are ordinary. But as long as we have the distributivity rule, some function types can behave like intersection types. And note that the two types are equivalent. So the idea of splitable type is to redraw the boundary between them and divide such function types into the same group as intersection types. Every splitable types can be taken into two parts and it behaves like an intersection of the two parts. Via this approach, the BCD problem is solved by revising the conventional formulation a little bit, just generalize the rule of intersection type to splitable type. And in this Perl, we extend the idea of splitable types to union types. Previously, there are ordinary types and splitable types defined according to intersection types. Now we also have union ordinary types and union splitable types. We define them based on these three distributivity rules. And similarly, once we have done this, we generalize the algorithmic subtyping formulation on intersection and union types by using the corresponding splitable types to replace the intersection and the union types. So we have seen splits for now. And what is the duality part? Actually, we have also seen the duality between intersection and union types in their logical correspondency, in the two sets of splitable types, and in their subtyping rules. dual typing is an idea extends subtyping by using a mode to define whether it's a judgment about subtyping or a judgment about supertyping. The mode can also be used to select between the two type constructors in the section and the union. So the two dual rules can now be unified into one. For example, if we instantiate the mode in the rule D and L by subtyping, we got A in the section B is a subtype of A. And if we instantiate it by supertyping, we then got A union B is a supertype of A. If you want to flip the mode, which means you want subtyping instead of supertyping, for example, you can use the D-dual rule. With the dual typing, we now get a very compact implementation in Haskell. In Haskell, we define a check function that takes a mode and two types. With a Boolean flag, the Boolean flag is to mark if it has already been flipped. So it initially is false. And if we want to check a sub top or a super type bottom, these are trivially true, as the first red arrow show. But if you want to determine if bottom is less than int, it will not be catched by this case and will go to the last red arrow, where the mode is flipped, and we turn to check if int is bigger than bottom. Int is bigger than bottom can then be taken by the first red arrow. And in the middle, we have two cases that deal with splitable types. Firstly, we try to split the right-hand side type under the current mode. If the mode is subtyping, we split it in the intersection way. If the mode is supertyping, we split in the union way. Only if we cannot split it, we will go to the next case and try to split the left-hand side type. So there is no backtracking across these cases. And the algorithmic subtyping formulation we have is actually derived from the dual typing formulation, which is an algorithmic version of the declarative dual typing. So we have two declarative systems and two algorithmic systems. In our paper, we prove that the four systems are all equivalent. Also, we have a Haskell implementation in both subtyping style and the dual typing style. We have a calc formalization that contains all the systems and the proof for our algorithm to be sound complete to its to the declarative system and the decidability of it. For our Haskell code, there are some inversion lemmas in our calc formalization that justify the order of rules. Note that the order of rules in the Haskell code really matters. For more details, please refer to our paper and the artifact. Thank you.
This is a presentation of the theoretical Perl. Leibniz equality is isomorphic to Merton-Luff identity parametrically by Abel, Cockix, De Vries, Tamani, and Wadler. I'm Philip Wadler. The paper was first published in Journal of Functional Programming, Volume 30, number E17 in 2020. I'm very pleased to be able to present it at ICFP this year. I think it's a great innovation that many conferences are bringing in, that papers published in other journals can also be published at the conference. So this paper is a story about two equalities: Leibniz equality, which we're going to write as an equal sign with a dot over it, and Merton-Luff identity, which we're going to write as three parallel bars. And it's well known that each of these implies the other. It's well known that that's a retraction, but what's less well known is that that's actually an isomorphism. To prove it's an isomorphism, we're not going to need to assume parametricity, what I've called elsewhere theorems for free. So from that free theorem, we will get that these are isomorphic. I think that's well known as a folk theorem, but this seems to be the first time it's been published in the literature. It's not a deep result, but it's a fun result and a great opportunity to learn a little bit more about these two different forms of equality. Now, if we go back to that paper for a moment, it's actually written as a literate Agda script. And so that means all of the Agda in it, like here's the main result. You can see it's typeset very neatly in color. But if we go to the source of this, you'll see that's all that code has been typeset between begin code and end code. And what that means is if I type Control-C, Control-L, Agda executes it. So you can see it's turned into color. You can see there's a wee window at the bottom with no error message in it. So that means it's type checked correctly. So we're guaranteed that all the code that we publish is absolutely correct. So that's a fantastic trick, and I encourage everybody to follow it. Let me give you just one other example. Here's a textbook that I'm a co-author of, Programming Language Foundations in Agda. This is published in GitHub on the web because the whole textbook is actually a literate Agda program, so you can execute it. Now, publishing on GitHub is great because it means when your readers find typos or other errors in your book, they can submit a pull request and fix that typo for you. And from this, I know that there are an embarrassing number of typos in this book. But I know one bit that has no typos in it, which is the bit that appears between begin code and end code, because that's executed Agda. I know it's type checked. I know there are no typos or other kinds of errors in it. So this is a great way of ensuring that we do what we are supposed to do and publish the truth. So that's literate programming in Agda. What this means is if you have a .lagda extension on your file, Agda will convert that to TeX. If you have lagda.md, Agda will convert that to .md, which is Markdown, which is how the textbook PLFA was done. Now, when you do literate Agda, I strongly encourage you to publish everything. So in this paper, we've published everything, even this little pragma at the beginning, which is a technical point, which says that we're not using uniqueness of identity proofs, and which means that everything that's done here is compatible with homotopy type theory, where you might have more than one proof that two things are equal. So I really encourage putting absolutely all the code in your published paper, because that avoids another kind of error, because it means your published paper can be read by Agda. And that means there's enough information there to explain it to Agda, and that means there must be enough information there to explain it to your reader. There are a number of times I've read other papers written in literate Agda. The authors of these papers were thinking, right, I will just hide some details to make things easier for the reader. But in my case, at least, it didn't make things easier. I couldn't follow what was going on until, fortunately, they'd also linked to the actual AGDA code. I could read that and discover what's going on. But if you just print the actual AGDA code in your paper, again, that's an error that can't occur. So I encourage people to consider printing just print literate AGDA and all of the literate AGDA. It's a great way to go. So let's actually look at Leibniz equality. So here's the definition. So this says, let big A be a type. Type is written SET in AGDA. And let little a and little b be values of type A. And then we're going to return another type. This type contains set, so it has to be in set 1. And how is this defined? So we have an implicit parameter a here. That means we don't need to write it explicitly. AGDA will infer that for us. And we give a and b, the two values that are equal. And then which type is it? The one that for every p, where p is a predicate over a. So that means it's a function from a to a type. And then a value here of p of a will be a value of that type. So evidence that the property p of a holds. And given that, we return p of b, evidence that the property b holds. So this is Leibniz equality. When are two things equal? They are equal if every property of one is also a property of the other. If you're a Star Trek fan, Mr. Spock expressed this by saying, a difference that makes no difference is no difference. So you'll notice that this seems quite asymmetric, right? We've got P of A implies P of B, but in fact, this is such a powerful notion that it is symmetric, and we'll see that in a moment. So first of all, right, we want to be reflexive. We want to always be the case that A is equal to A. What does that mean? Given an arbitrary P and proof that P of A holds, we need to return proof that P of A holds. Okay, that's very easy. It's also transitive. So given, now notice here, A equals B with spaces is the predicate. A is equal to B. And then by convention in AGDA, we just write the same thing without spaces. This is typeset all in black. It's just a variable name. So it's a lot like Lisp. Spaces are very significant, and you can actually have symbols in the middle of names. So A equals B here is just a variable name, but its type, in fact, is this one, A equals B. So this is evidence that A equals B. This is evidence that B equals C. And now we need to return evidence that A is equal to C. What does that consist of? Well, it says, give me an arbitrary predicate P, give me evidence that P of A holds, and now I need to return evidence that P of C holds. So how do we get that? Well, A equal B applied to P and P of A gives us evidence that P of B holds, and then B equals C applied to P and evidence of P of B gives us evidence of P of C. So function composition gives us transitivity. Now, the fun one is symmetry. So now, given evidence that A equals B, we want to return evidence that B equals A. So we've got evidence that A equals P. We take our arbitrary predicate P, and now we need to return function that given evidence of P of A returns evidence of P of B. So that's what Q of B is going to be. So we're going to define a new predicate Q in terms of P. So Q of C holds if P of C implies P of A. And obviously Q of A holds, right? Because that says P of A implies P of A, so that's just the identity function like before. But now, right, we can take not just any predicate P, but any arbitrary predicate, so we can use Q, which depends on P, and then A equal B, given predicate Q, and Q of A, evidence that Q of A holds, returns something of type Q of B, evidence that Q of B holds. But Q of B is just P of B implies P of A, which is, exactly what we wanted to show. Therefore, Leibniz equality is also symmetric, one of my favorite proofs. So Merton-Loaf identity is defined in this way. The type A equals A is inhabited by reflexivity. And we can pattern match on that, so it's very easy to show symmetry, because when we pattern match on reflexivity, then it knows the only way that A equals B can hold since it's reflexive, is if B is in fact A. So this becomes A equals A, and now we've got A equals A implies A equals A, which is, again, A equals A is proved by reflexivity. Similarly for transitivity. So that's all very straightforward with Merton-Luff identity. We'll need one other thing, which is extensionality, which just says if for all A, f of A is equal to g of A, then the two functions f and g must be equal, and we'll just postulate that because it's not built in to AGDA. So now we actually get the equivalence. We can show that A equals B in Merton-Luff implies A equals B Leibniz, and that's easy. So A equals B we pattern match against Reffel. Now we need evidence for A equals A, and that's easy, because given P and P of A, we just return P of A. The other way around, we've got Leibniz, and we need to show Merton-Luff. It's very similar to the proof of symmetry, but now, instead of taking Q of C to be P of C implies P of A, we're going to take it to be A is equivalent to C. Okay, and then obviously Q of A holds by reflexivity. And then again, right, A equals B on Q, and Q of A transposes that to give us a proof of Q of B, which is A is equivalent to B, which is what we wanted to show. So very similar proof. Left inverse just follows immediately by simplification. Very easy. To show right inverse, we need parametricity. So here's the theorem for free that corresponds to the type of Leibniz equality. So our for all P now becomes for all P and all P prime, and all relations are that for an arbitrary C of type A gives evidence that P of C and P prime of C are related. And then similarly for the rest, I won't go through that in detail. You can find the technical details in the paper. And then finally we get the proof of right inverse. Again, I'm not going to go through that in detail, but it uses parametricity. It uses exactly the same Q of C that we used to show that J exists, and a suitably defined relation. I'll leave the details of that for later. And then by applying extensionality, we actually get that's an actual inverse here, because before we just showed this when applied to arbitrary P and P of A, but here we can show it via extensionality. And that's it. If we go back to the code, you can see that this has all been written again as literate AGDA, and indeed that main result is true. Thank you for your time.